All right, it's 2:40. See, some of you showed up on this election counting day, so thanks for attending. We seem to have had a lull in the vote reporting, so what better excuse to take a break and think about something different like the planet Jupiter. So that's what we'll do. A couple of announcements. Let's see, homework 7 was due yesterday. Hopefully you all got that in. Homework 8 is currently scheduled for next Wednesday. Depends on whether I can get through all the material. I'm running a little bit behind, so I'm gonna pick up the pace a little bit. At least I'm gonna try to. But currently it's scheduled to be due on Wednesday. Office hours next week, I've pushed up till Tuesday, so you can have an office hours before the homework is due. And the final exam, after looking at how everyone voted last time, it will be on Monday, November 23rd at noon. That's when I'll release it on WebAssign, and it will be due 24 hours after that. I think that's it for announcements. Any questions? Okay. So let's take a look at this warm-up question. And it uses skills that we've learned before, but will be relevant to today's lecture. So we have a planet, and it's 11.2 times the size of Earth, and it's 318 times the mass of Earth. What is the escape speed from that planet, from the surface of that planet, in kilometers per second? And I've given you Earth's escape speed in kilometers per second, which is 11.2. Coincidentally, same as the radius, but that's just a coincidence. So we have 3 responses so far, and I'll give you all like 40, 50, 60 seconds to work through it, but go ahead and give it a go. Another 10 or 15 seconds. Get your answers in there if you got them. Okay, let's see how we're doing. Looks reasonable. Most of you got the right answer. Let's see, I got a couple 60s there. 2 bins that say 60. I wonder why. But anyway, yeah, most of you answered something up here around 60. We have a few other answers, so let's go through it. So escape speed, this is one of the 3 things that we can calculate given the mass and radius of a world. As we've been encountering new worlds, whether they're moons or planets, I've been giving you their masses, their radii in Earth units, and asking you to calculate sometimes the average density, sometimes the surface gravity, the weight multiplier, and sometimes the escape speed. And you may remember the equation for escape speed, let me open this up here, is mass over radius, square root of that quantity. And if you put the mass and the radius in Earth units, what will come out is the escape speed in Earth units. So you plug in the mass of 318 Earth masses, radius of 11.2 Earth radii, And so it's just 318 over 11.2 and square root of that ratio. And that is the escape speed, and Earth escape speeds comes out to be about 5 1/3. So for this world, you're going to have to travel 5.33 times faster to escape from its surface. And I asked for it in kilometers per second, so you need to know Earth's escape speed, and that was given here, 11.2 kilometers per second. So overall, it comes up. Now I see someone got the 5.3, so that explains the ratio, but the last step there is multiplying it by Earth's escape speed, and it gives you about 60. So 60 kilometers per second to get off this world. Anyone want to guess which world this is? 300 times the mass, 10
Would
times.
it be
Jupiter.
Saturn?
Jupiter, yep. And that's the world we're going to study first. Today, we're going to focus on Jupiter. And so this big escape speed, it tells us a lot. Think about atmospheric retention. This is basically why the gas giants are the way that they are. They have these huge escape speeds, and so you can retain your atmosphere. Remember, you lose an atmosphere if the particles are moving around, if the particles are hot, moving around fast enough that they can escape, or at least some small fraction can escape, and then it's a gradual process. These worlds are very far from the sun, so it's going to be cool out there. Temperature is going to be low, so the particles in the atmosphere are not moving around very quickly, and then the escape speed is so huge, they're not going to be able to beat that. And that goes not just for heavy particles in the atmosphere, like here on Earth we have O2 and N2, and we can retain that, but we can't hold on to our H2 and our helium. They're lower mass, they bounce around more quickly, and so they can escape into space. With the gas giants being colder, even those lightweight particles are moving around too slowly that they can't beat this ginormous escape speed. And so you can retain hydrogen and helium out there as well. And you may recall most of the universe is hydrogen and helium. We talked about the big five: hydrogen, helium, then after that, carbon, ammonia, methane. And here on Earth, we can retain the carbon, ammonia, methane, but not the hydrogen, helium. Out among the gas giants, out beyond the asteroid belt, you can retain hydrogen, helium. Since that's the most abundant thing in the universe, you can very quickly grow these very big planets. So that's the biggest difference, and the explanation of the biggest difference between the gas giants and the terrestrial worlds. Okay, so on to our first gas giant. We set them up last time. So we'll begin with Jupiter, closest one to us, closest one to the sun. And here's a picture of it taken from Earth. It's about as good as you can do from Earth. I've seen a little bit better under like really great atmospheric conditions, but I've seen a lot worse too. So this one's decent. It's a little bit blurry, but that's because of the atmosphere. If you go to Jupiter and go into orbit, and you don't have to worry about the atmosphere, and you're really close, you can get much greater detail, tremendous detail. You can see this is really crisp, and you can see not just the banded structure, but details in the banded structure. Tremendous information there. Here's a slide comparing Jupiter to Earth. We said Jupiter is 11.2 times bigger than Earth. So that's what that looks like. It makes Earth about as big as the Great Red Spot. Excuse me, or actually the red spot's a little bit bigger than Earth. And we'll learn, these spots, they're essentially massive hurricanes. So it's a hurricane bigger than our entire planet. Let's take a look at some of the numbers here. So this is in the ebook, lesson 8, same kind of table that we looked at for the terrestrial worlds. Here we have Jupiter, again, 11 times the radius, 300 and some times the mass. So we can calculate our three favorite quantities. You just did this for escape speed, 60 kilometers per second. For average density, that's mass over radius cubed, which you can then multiply by Earth's average density, and you get 1330. So kind of close to 1,000. And I said if something has a density of 1,000, it's either water or ice. That's one possibility. And the other possibility is it's gravitationally compressed gas, and that's what we're looking at with the gas giants. Some of the moons will be water and ice and will have similar densities, but with the planet itself, it's gas, a whole bunch of gas gravitationally compressed, but about the same density as a glass of water on average. Then you have the surface gravity, that's m over r squared, and here we just kept it in Earth units. And you notice Jupiter is kind of interesting. Well, first I should back up. What is the surface of these worlds, these gas giants? It's gas like all the way down or almost all the way down. We'll learn there is probably a core in there somewhere deep down, but we'll never reach it. So with the gas giants, when we're talking about the surface, we're talking about the cloud tops, where it becomes opaque. You know, the gas is transparent above and opaque below. We call that the surface. That's the convention. And so if you're, I was going to say standing there, but you can't stand there, you just fall. But if you're, I don't know, on an orbiting platform or a platform that's flying through the atmospheric layers there, you would feel 2.5 times heavier than you do here on Earth, which is, you know, a lot. You wouldn't want to endure that for too long. And you can see the other gas giants here, Saturn, Uranus, Neptune. They all have a surface gravity similar to Earth's. So you'd be able to withstand that, work in that environment. But Jupiter is different. It has a couple consequences. One is it will squeeze the cloud layers really thin, as we'll see. And that contributes to the unique coloration that we see. Since the cloud layers are so thin, we can kind of peer through weak spots in some of the upper layers and see lower layers where the temperatures are different and the chemical reactions are different, and so the colors are different on Jupiter than, for example, Saturn. We'll come back to that. Another consequence is we've sent an atmospheric probe into the upper atmosphere of Jupiter, got crushed pretty quickly. That higher gravity, there's more squeezing. Once you get deep enough down, all the atmosphere above is squeezing down on you. And so we can't send probes as deeply into the atmosphere of Jupiter as we could these other worlds. And lastly, another consequence, this one's kind of fun and it's futuristic. It's nothing that impacts us now, but eventually the gas giants are going to be great resources for us. You know, right now, the global economy, as we talked about when we talk about global warming, is based on the burning of fossil fuels. We're trying to switch over to clean energy sources like solar and wind and geothermal. But the ultimate energy source for human civilization will be fusion, nuclear fusion, which is different from our nuclear power plants. Our power plants use nuclear fission, where we take uranium and plutonium and things like that and split it apart to release energy. It's a messy process. The byproducts are radioactive and dangerous, all sorts of downsides there. But fusion is that's the opposite end. That's when you take small particles and squeeze them together. You can also get energy out of that process. That's how the sun is producing energy. It's squeezing hydrogen atoms or hydrogen nuclei into helium, producing energy. So it's always been like the ultimate goal of scientists to figure out how to do this, how to reproduce the conditions, the inside of the sun. And we can do it. We can do it easily in an uncontrolled fashion. Those are our hydrogen bombs. But to do it in a controlled fashion where you release this energy without destroying the device you built to do it, it's challenging. We've had experiments that can do it for like a fraction of a second and produce more energy than it took to run the experiment during that time. But we haven't maintained it for long periods of time yet. Anyway, that will be a goal. That is the goal, and maybe it's decades away. We've been saying that for decades, and we're still saying that. So it's a challenging problem. But sometime this century, we'll have it mastered, and sometime after that, it will be commercial. You know, we'll get to the state that you could do it efficiently, commercially, and then the fuel source is variants of hydrogen and helium, isotopes of hydrogen and helium, like deuterium and tritium and helium-3. And hydrogen and helium are the most abundant things in the universe, and our biggest supply, and finally, a long tangent here, but coming around, our biggest supply are the gas giants. So once we eventually figure out fusion, we'll start by scraping the surface of the moon. We have some stockpile of it there in the lunar soil. But eventually you'll want to go out to the gas giants and mine it there. We'll want to set up orbiting platforms and suck it out of the atmosphere. The isotopes are kind of rare, so you have to go through a lot of hydrogen and helium to extract it, but you do it and send it back to Earth. It's centuries away, but that's what our economy will likely be like and based on at that point. Anyway, Jupiter's closest, so that'd be ideal, but the surface gravity is so much worse there. We can't work under those conditions, and maybe we send robots that are really sturdy, but it may be easier to mine Saturn, Uranus, Neptune than Jupiter because of that high surface gravity. Anyway, wild tangent, but kind of a fun one to think about. All right, back to the slides. So those were the bulk properties. Let's move on to the interior of Jupiter. And, how can we figure out what this looks like? Well, we have sent a probe, but it only went about 150 kilometers down before it was crushed. And so that's nothing. The probe didn't tell us anything except the properties of the cloud tops for the most part. The way we do it, we use the density. That gives us some information. But we measure the oblation of the planet. It's a ball of gas. And if it were sitting perfectly still, gravity would pull it into a perfect sphere. But it's not perfectly still. It's rotating pretty quickly. Jupiter rotates about once every 9 to 10 hours. So it's spinning much faster than Earth is, despite its immense size. Being a ball of gas, it's going to become oblate, a little thick around the middle. You have the fastest speeds on the equator, so it's going to want to fly out. And so all planets do this, even the rocky planets, even our planets, a little thicker around the middle. That's why we precess, if you recall, than we are from pole to pole. But being just a ball of gas, you get more of this. And if it's a pure ball of gas, there's a certain oblation you would expect. But what we measure is a little bit less. And it tells us it's not a pure ball of gas. There's got to be some kind of rocky, denser core. We combine that with the density information, and we can figure out what the center is like. I'll show you that in a second, but the oblation for Jupiter is about 6%. It's 6% thicker along the equator than pole to pole. I can show that. Here's afterglow. So if you're in the lab course, you're really familiar with this. This is, I have it up from the last section, but here's a picture of Jupiter that was taken. It's not even a great picture. It's kind of fuzzy. But I'll use the ruler tool here and kind of measure. This is along the equator. I got to estimate where the edges are a little bit there. But let's see, that's about 39 arc seconds across. And from pole to pole, about 36. So you can see it is oblate. It's a little bit thicker. In fact, let's figure this out here. 39 divided by 36. I measured about 8%, but it's not the best picture. If I had a better picture and did it more carefully, I would have gotten about 6%. Anyway, it's thicker around the middle. And so as I was saying, here we go. You can use that to figure out what the interior is like, and it's something like this. Deep down, there has to be a denser core, and we think there's some metals in there too, but primarily rocky material, icy material. But above that, then you just have primarily hydrogen and helium mixed. And there's water, ammonia, methane mixed in as well, but our big five. But you have this huge atmosphere, and it's primarily hydrogen and helium. Now let's focus on the hydrogen, because the hydrogen can have two different forms. It's the same stuff, it just behaves differently under pressure. Up here we have regular molecular hydrogen. That's two hydrogen atoms stuck together, giving us H2, the H2 molecule. But deeper down, they get squeezed closer and closer together until they're all essentially touching like a fluid. So here we have molecular hydrogen, the little pairs bouncing around with space between them. But you get deeper down with all that pressure, and they're squeezed right on top of each other. They roll around each other like a liquid would. Even though it's gas, behaves as a fluid. And since they're so close, the electrons can hop from atom to atom. So if the electrons can move, it's like a metal. You know, metals, electricity can move through them. Electrons can move through them. They're conductive. So this is a conductive fluid. It's a different type of conductive fluid than we saw in the inner solar system. You know, for Earth and the other terrestrial worlds, we're talking about liquid iron, iron in a fluid form in one of the deep layers of these worlds. Here, there's maybe some of that deep in the core, but the bulk of what we're talking about here, the metallic hydrogen, is a conductive fluid, and Jupiter is spinning very quickly, once every 9 to 10 hours. So what are we going to have? Conductive fluid, rapid rotation equals, shout it out.
Atmosphere?
Magnetic field.
Damn, sorry.
Yeah, you're right. It's the atmosphere producing the magnetic field. And it'd be a very strong magnetic field because that is a lot. The whole pink area here is the metallic hydrogen. It's a depth of 20,000 kilometers, 3 million atmospheric pressures, and that's when it becomes conductive. And there's a lot.
Hey, Dr. Reck,
Yeah, go ahead.
I have a question. So is the metallic hydrogen right below like the cloud surface, or is there space in between the clouds and the metallic hydrogen?
Yeah, it's pretty deep. The cloud surface only, the cloud layers, which we'll see, they only go about 100 kilometers deep. You got to go about 20,000 kilometers deep before you get the metallic hydrogen. And of course, we've never probed down there, just our understanding of physics and chemistry and molecules, we can calculate when it would achieve this conductive property. So you get a big magnetic field. It's about 14 times the strength of Earth's. So it's the biggest in the solar system other than the sun, which is like pure, the sun is all metallic hydrogen. So 14 times stronger. You know, with the terrestrial worlds, we only had one, Earth, that had a strong magnetic field. And we'll see with Saturn, Uranus, Neptune, they have Earth-like magnetic fields, so strong as well. But Jupiter, it's super strong, 14 times stronger. And in this figure here, we see, you know, the sun's off on the left, and it's producing the solar wind. There's material streaming off the sun always, and some of its charged particles moving quickly, and it runs into this magnetic field. And a lot of it gets trapped by the field, and we'll come back to that. But some of it shapes the field, pushes on the field. And this is how big it is. It goes all the way out past Saturn. It stretches it out into this long tail that we never expected. We just found it by accident with Pioneer 10, the first probe that we sent out to Jupiter. It went around Jupiter and then went off into deep space. But it passed behind Jupiter again, because Jupiter's moving over here and it was moving over there. And then it detected the magnetic field again. Total shock. So it goes all the way out past Saturn. Sometimes Saturn moves through Jupiter's magnetic field, if the alignment's just perfect. But most of the particles will get trapped in the field and funneled to the poles, just like on Earth. And so you're going to have aurora borealis in the north, aurora australis in the south. I'm not sure if those terms apply to other worlds other than Earth, but yeah, you get aurorae. And here you see a visible light picture in the back and superimpose some ultraviolet pictures. So this is where the magnetic field lines intersect the atmosphere. It's glowing in the ultraviolet. And we can even go to the X-rays. This is taken with the Chandra, NASA's Chandra X-ray telescope. You see where the field lines are entering the atmosphere. And it glows here. Something called synchrotron radiation, which you get when you have electrons in a strong magnetic field. Last bit about the interior is its heat. And so we'll talk about this with each of the gas giants. Now, each of these planets, like anything orbiting the sun, is absorbing light from the sun, and that heats it up to a certain level. But when we check the surface temperature of these gas giants, 3 of the 4 are hotter than you would expect from our temperature equation. You know, we have this temperature equation. All the gas giants are rapid rotators, well atmosphered. So you can use that particular equation. All you need to know is the distance from the sun and the albedo, and you can calculate how hot the planet should be. But then we can take a spectrum and measure how hot the planet is. And for 3 of the 4 gas giants, they differ. So that means 3 of those 4 have an extra source of heat, an internal source of heat. Unfortunately, it's a different story for each one. There's no consistent pattern, no theme here that makes it easy to learn. In the case of Jupiter, it's heat of formation. And I'll come back to that. Let me actually throw some math up on the doc cam. So I was saying the temperature of Jupiter, I didn't say it, but it's 125 Kelvin. We observe it, take a spectrum, we can measure its temperature through all the different methods we talked about in lesson 3. The temperature that you get from the rapidly rotating planet temperature equation that you've been using is 105 Kelvin. Check my notes, make sure I got that right. Yep. So there's a difference here. So more energy is coming out than should be. How much more? We can use Stefan's law for that. These are thermal emitters, so go back to our black body equation. Stefan's law says the energy flux, the energy that's emitted per square meter per second, is proportional to temperature to the 4th power. So if we want to know how much more energy is coming out than we would have expected just from the sun heating it, it's 125 over 105 to the 4th power, which you put into a calculator, it's about 2. There's twice as much energy coming off this planet as is going into it from the sun. And that's what this figure is depicting. Here's the sunlight coming in, here's heat coming out, but you have just as much heat coming out from the interior. And as I said, the source of heat for Jupiter is its heat of formation. As I've talked about before, planets form hot. As stuff is falling in from space and becoming part of the planet, picks up speed because of the gravitational force, and then it hits whatever's there, transferring that energy into heat. So as planets build up, they build up quite hot. And we also talked about small planets, small worlds lose their heat quickly, and large ones lose it slowly. And we did a calculation last time. Small worlds will lose that heat of formation quickly and then just become whatever temperature we expect from the sun and any greenhouse effect. Jupiter is the biggest of the planets, and it's so big that it's losing its heat super slowly. And it still has heat from its formation 4.5 billion years ago. It's losing 1/1,000,000, the 10 to the minus 6 degrees Kelvin each year, just a smidgen. So it still has some of that heat of formation, and that's why it's hotter than we would have expected. Okay, that is the interior of Jupiter. Any questions before the atmosphere? Okay, atmospheric layers. So it's a very busy surface. There's a lot of stuff going on here. We're used to seeing these pictures with all the swirls and the banded structure, and it looks all very kind of still and majestic, but it's actually quite busy. Let me put up a little animation here. It's this one. Nope, it's oh, there it is, sorry. This was taken by one of the Voyager probes as it approached Jupiter back in the 70s. You took lots of images. This is every image where the great red spot was facing the spacecraft. So, you know, it's rotating between every frame, and it takes just that image and pieces it together. So these are each about 10 hours apart. And you can see the clouds are moving. Some are moving to the right, some are moving to the left. The spot swirling about, it's very busy. There's a very active weather pattern going on Jupiter here. So we have this banded structure, and some of it's moving to the right, some to the left. We call these zones and belts. And then we also have the spots, and here's the great red spot. And these are essentially hurricanes. So I'll put some info up here. We have zones, we have belts, we have spots. The zones are regions that are, they're moving in one direction, but they're also high elevation and cold. The belts are lower deeper into the planet, and hence warm. And then the spots, as I said, are just hurricanes. Come back to that. The zones and belts, this, we can kind of get a feel for this. If we think back to Earth, Earth has these convective cells. A slowly rotating planet has two, one in each hemisphere, like Venus. The faster rotating it is, they break apart into these cells that stretch around the planet. And Jupiter is even bigger and rotating faster, so it breaks apart even more. On Earth, it's 6 nice, well-defined, banded cells here. Jupiter, there are more of them, it's more complicated. But that's basically what it is. It's the Coriolis force and the rapid rotation stretching it around. You have regions between them where you can peer down and see warm gas coming up, and other places where it's sinking and that gas is already cold and it's high up getting ready to sink. So you have high up cold regions, you have places that you can peer down and see the low down warm regions, and these are the zones and the belts on Jupiter. And here you have a heat map taken with an infrared camera where the dark regions are the cold regions, so those are the zones. I always check because I always get them backwards. And these would be the belts. And also you can see the great red spot here, it appears dark. That means it's high up in the atmosphere where it's cooler as well. So these hurricanes are riding high. Here is just a picture, Earth compared to the great red spot for scale. And let's see, I have a little low resolution movie clip here. Kind of lets you see how these hurricanes form. It'll take a second for the image to load in. There we go. They always form between the zones and the belts. The zones are going one way, the belts are going another, so you get a little whirlpool that can develop in between. And that's what's going on here. Get rid of that. And yeah, and you can see it here with arrows, gas flowing one way, gas flowing another. So you get these little swirly patterns, little and bigger than the planet Earth. And they're essentially hurricanes. And on Earth, the hurricanes, they form over the water. But what stops them? What stops a hurricane? Makes it go away on Earth?
Land?
Land. There's no land here on Jupiter. I mean, they may be like way, way deep down, but these hurricanes are way up here in the cloud tops. So land's not going to stop them, and nothing stops them. The only way you get rid of a hurricane on a gas giant is if it merges with other hurricanes and just becomes a bigger hurricane. And so that's what happens. Here you can see some little ones. These little white spots are little hurricanes that formed, little spots. And then they kind of moved together and merged into what was called the Red Spot Junior, like a little mini red spot. And I think Red Spot Junior has now since merged with the Great Red Spot. All this took like half a decade, but that's the procedure. And you may think the Great Red Spot would get bigger and bigger and bigger, but it has like an ideal size. If new things merge in, then the outer layers peel off and become part of the zones and belts around it. And this may explain why the Great Red Spot, Galileo saw it. So it's a long-term structure, maybe a permanent structure. Hurricanes come in and feed it, and it dissipates some of its outer parts to the bands around it. Now, the hurricanes, we see them mostly in the southern hemisphere. And they think it has something to do with the Coriolis forces, that it rotates the gas one way in one hemisphere and the other way in the other hemisphere. And, it spins it one way in one hemisphere, spins it the other way in the other hemisphere, just like here on Earth. That interacts with the fast rotation in a particular way. It gives you hurricanes in the south, higher density regions, but openings, holes in the north. And that's what these dark spots are. These are openings in the cloud tops that you can peer down and see the deeper layers. Let me see, there's something here I wanted to hit that I forgot, but this is a good time to bring it up. And the deeper layer looks darker. The coloration, the wildly different coloration that you see across Jupiter is just because of depth and heat. You know, if you can see down to greater depths, it's warmer down there and you have different chemical reactions. These are usually different reactions with sulfur for the most part, giving you different colors. So you look down there, it's a little bit darker. Higher up, it's maybe lighter. And when we look at Jupiter, we see things at different heights and different heats, and hence you get an intricate pattern of colors. Anyway, these holes, we sent a probe through one of them. It rode on the Galileo spacecraft in the 90s. It's an atmospheric probe. And I think this is a little animation of it being sent. It's a long animation. I'll just kind of jump ahead here. There's the Galileo probe approaching Jupiter. Sorry, I'll back up. I skipped. There's the Galileo probe. There's Galileo, the spacecraft. The fast forward doesn't work on this one. The probe has to separate out at some point. Did I miss that? Yeah, okay, so right at the beginning, the probe separated from the spacecraft, then did its own thing. The spacecraft went into orbit. There it's going into orbit. The probe is descending, and of course this is animated, and enters the cloud tops. And it's a really dense, thick atmosphere. Slows it down a lot. We use the parachute. Because of the thick atmosphere, it took a long time to descend. So we got data for a long period of time until it finally got about 150 kilometers deep, and the atmospheric pressure crushed it, the high surface gravity. And it happened to go through one of those holes. It would have worked even if it didn't, but it just happened to go through one of the holes. And here's what it found. 3 different cloud layers: ammonia ice, ammonia hydrosulfide ice, and water ice. So 3 different types of ices, but you know, ammonia, water, those are some of our big elements. This is a different variation, ammonium hydrosulfide. But these ices are slightly lower density, so they're like clouds. And they float over top of the main body of our big 5: hydrogen, helium, methane, ammonia, water. And it's these all the way down to the core. So it made it down into that layer before it got crushed. Okay, that is the atmosphere. Questions about that? I got to get through 2 moons today, so you're at the same place as the other section. So I may end up going a few minutes over. Let's move on to the moons. You know, we're inside out, so we started with the interior and then the atmospheric layers. And so now we're out to the moons. And first we encounter the Galilean satellites, the 4 big moons of Jupiter. And there are only 7 big moons in the solar system. 4 of them around a single planet is pretty impressive, but it is the biggest planet, so maybe not surprising. And we studied them in great detail with the Galileo spacecraft. It went into an orbit like this. They would keep swooping into the moons and having close encounters for like a decade. So we had lots and lots of close encounters with these moons and took these, you know, amazing close-up images of them. And they are, and you'll need to know this because you're going to learn a little bit about each one: Io, Europa, Ganymede, and Callisto. So let's start with Io. It's the one that's closest in. Oh, actually, before we get to that, let's just talk about them as a collection. They are like a little mini solar system, if you want to think of it that way. Instead of the sun at the center, we have Jupiter, and then we have these moons. And in this, you know, the farther out you go, the bigger the spacing, like in the solar system. They're all going around counterclockwise, orbiting. They're rotating counterclockwise, like in the solar system. For the most part, the planets rotate counterclockwise. They all orbit counterclockwise. Similarities there. Also, the density is decreasing. You can see the density here decreasing the farther out you go, like in the solar system. But there are differences as well. All of these moons are tidally locked to Jupiter. Just like our moon is elongated, and that elongation wants to point towards the central planet. The same is true with the moons of Jupiter. All of them are tidally locked. That's different from the solar system at large. And also the surfaces are different. Io has a rocky surface, like the terrestrial worlds do, but the others are covered in ice, and that's a little different, water and ice. Now the tidal locking is even more powerful, at least with the moons that are close in. Like Io is extremely tightly locked. It's a small world. It's so close to this big, massive world that the tidal locking is pretty extreme, just to convey how close it is. Now, here's a picture. We've seen it before. This is standing on Earth, looking at the moon. But imagine if you were instead standing on Io, looking at Jupiter. This is what Jupiter would look like in your sky. And since you're tidally locked, it would just stay put. It wouldn't move. You know, your side is always facing Jupiter, so it would just sit there. And that's what you'd see every day. And I made this a long time ago. It took like an hour and a half to make this in Microsoft Paint. So I'm not sure if I should be proud of that or not. Anyway, yeah, so the tidal locking is a difference. The surfaces are different. So let's start with the moon Io. And again, small world close to a very, very big world. I like this picture. It really kind of puts it in perspective. You've seen this picture before. We saw it in lesson 5 as I was doing a quick tour of the solar system. This is the first picture we ever took of Io, and by Voyager 1. And to our surprise, there are 2 volcanic eruptions going on. Here's another picture taken with Cassini on its way to Saturn. This is the thing we put in orbit around Saturn, but it had to do a gravity assist, a slingshot around Jupiter, and took a few pictures, and again, more volcanic eruptions. Here's a picture from Galileo, the spacecraft, of the dark side of Io using an infrared heat camera, and they're just eruptions all over the place. This is a very volcanically, geologically active world, probably the most active in the solar system, probably even more active than the surface of Venus. So why is that? Because it's a small world, and we learned that small worlds lose their heat and become geologically dead pretty quickly. But this one's very active, despite being tiny. And it's because of the combination of tidal locking, but interference by another body. Like our moon is tidally locked to Earth, and that doesn't warm it up. It locks its rotation, but you know, it's the temperature it should be given its distance from the sun. But with the moons of Jupiter, they're not just there by themselves. Here's Io tidally locked to Jupiter, but then Europa swings by and it messes up that tidal locking in such a way that creates friction and heat. So this is how it works. Actually, Europa's not swinging by. Io's closer, it moves faster. So here's Jupiter, here's Europa. Io swings between them, and it pulls on the orbit, tugs the orbit a little bit, makes it not circular. And we learned from Kepler's second law that the farther you are away from the central body, the slower you'll orbit. And so the rotation is locked in. This is kind of like Mercury, actually. The rotation is locked in on this side, but when you come over here, you're going to be orbiting slower than you're spinning. And so you're going to get, and I'll try to demonstrate it here. I'll use the dot cam. The squishy ball here. Let's see, let me get this right. So there are words on there. I'll have it facing the camera, and I've squished it with my hand, so it's kind of elongated. And if it's tightly locked, that always faces. You probably can't tell. I'm rotating my hands to keep it perfectly faced. But let's say you're Jupiter, I am Europa, Io's passing in between. You get this kind of rotation whenever it passes close to Europa. And so, you know, I got the squishy ball, but I can just do that with my hands too, every time it passes. If you take your hands and do this, you know what's going to happen. It's going to warm up. It's friction. And so that's what's going on here. Every time it passes between Jupiter and, I explained it there. You can see it here in the picture too. So let me explain the picture now. So it's rotating, you know, it's orbiting slower here, but rotating at the same speed. So it gets a little misaligned, but Jupiter squeezes it. And that extra squeezing, that's the friction, and that's heating the interior. It's not enough to melt the core, but it will melt the mantle. the entire mantle is molten, and that's why it's so volcanically active. And the volcanoes, they spit out lava that melted any ice or water on the surface, evaporated it. So you have a rocky surface. This is another little clip. This is from the New Horizons spacecraft. It went to Pluto, but again, a gravity assist around Jupiter, took 5 pictures. And so these are the 5 frames over and over, and you can see the volcanic eruption moving. And it's impressive. It really goes pretty far off the world, but it's because the world is so small and the gravity is so low. A lot of it falls back down, but some of it gets trapped in Jupiter's magnetic field, creating something called the Io plasma torus. Io is so close to Jupiter, it's orbiting in Jupiter's magnetic field. So as the volcanoes spew out material, some of it's hot and charged, the magnetic field grabs those charges and pulls them forward. The magnetic field is tied to Jupiter's course, so it's spinning every 10 hours. Io takes like a day to go around. So these particles are being pulled off of Io forward all the way around, and comes around, hits Io on the backside. And it's called the Io plasma torus, and it's a place we'll never want to go. The radiation levels are crazy, and it'd probably kill us being in there. Here's another little clip. This is made with radio telescopes. In the Io plasma torus, it glows in the radio. And so that's band there. Io orbits there. Okay, 4 minutes. Let's see if I can get through Europa. Any questions about Io first? Okay, Europa. This is the smallest, by just a little bit, of the Galilean satellites. And it's covered in ice, and it's pretty fresh ice because it's so white. The longer ice is exposed to space, the darker it gets. Micrometeorites collect on the surface. This is gleaming white, but there are all these cracks all over it. And it's pretty easy to explain. It's tidally locked to Jupiter, but whenever Io passes by on one side or Ganymede on the other, it does the same thing. It messes it up. So imagine taking the squishy ball here, the weight ball, dunking it in water, putting it in the freezer so it has a nice coat of ice, then go like that to it. You're going to get cracks all over the ice. And you see them here. This is slightly color enhanced, but they are stained. There are minerals there's an ocean under there. The minerals, they go up and get stuck in the cracks and change their color. And this is just enhancing that so you can see them. But you can follow the cracks. They don't go back to impact craters or anything. It's the tidal forces cracking the ice. Here's some more evidence that there's water under there, an ocean. If you look at the cracks, you see, like focus in on this one here. You see the double line, and then it shifts, and then it shifts. So what happened is a crack formed, but then the ice broke up and floated around and refroze. And we see that on Earth all the time. We call them ice flows, where the whole thing can be solid, it breaks up, shifts a little bit, and refreezes. And you can see that in the shifting pattern of the lines on the surface of Europa. And occasionally we do find an impact crater, and it looks like water just came out and then refroze, erasing any pattern that was in the ice before. And so this will refresh the ice, but mostly the cracks and the flows, when the water gets out there, gives us a new surface, so that it's constantly being resurfaced and recracked. So here's what we think it looks like. Metal core, rock. Being farther from Jupiter, the tidal force isn't as strong, so the tidal heating's not as strong. The rock, it's not hot enough we're not warming it enough to melt the rock, but we are warming it enough to melt ice. And so you have that water ocean. And we know how deep it goes as well. And this is kind of weird, but it has a secondary magnetic field. That water is not just water, it's salt water, like our oceans. And salt water doesn't make a magnetic field on its own, but if exposed to one, it can make another. And so Jupiter's magnetic field activates a second magnetic field in this salt water, and we've measured it, and we can use that to figure out how deep it goes. It goes 100 kilometers deep. To put that into perspective, our oceans on Earth go about 4 kilometers deep. So these are really, really deep oceans. Now we have a lot more surface area, but comparatively shallow oceans. Europa has less surface area, but much deeper oceans. If you do the math, there's twice as much water on Europa than on Earth. And so this is really interesting because it's water in a liquid form, which is one of the requirements for life. If you ask experts where they expect to find life in the solar system, you may think they'll say Mars, and they say, yeah, maybe some microbes, maybe they're all dead and fossilized. But if you want to find like life today, and maybe complicated life, and not just microbes, but something that evolved into who knows what, a multicellular life, you probably want to look at Europa. Now, life requires an energy source, and it's far from the sun. It's not going to be the sunlight. It's going to be the tidal heating. At the bottom of the ocean, and this is from the bottom of Earth's ocean, we have these geothermal vents where energy is being released, chemicals are being released, and there are life forms that evolved around these geothermal vents. They don't use sunlight as their energy. They use geothermal energy as their energy source. And the bottom of Europa's 100-kilometer deep ocean is going to just be covered with these. And so there could be life on Europa, perhaps very different than the life here on Earth. No one knows. We'll have to go there. We'll have to cut through the ice, and we'll have to go down deep. So technologically, it'll be challenging, but someday we'll know. Okay, so I got through everything I wanted to. Any questions about anything? Well, if you do, I'll stick around. Otherwise, thanks for coming. You can get back to your election watching now.
Thank you.
All right, have a good weekend.
You too.
Thank you.
Thank you.
Thank you.
I do have a question about the tidal locking.
Yes.
So do the moons have the same effect on Jupiter as like the moon has on Earth with like the tides rising and falling?
Yeah, they would to a small degree. It's just Jupiter's so much bigger and more mass and more gravity that it's going to be a much, much weaker effect. Like we talked about how our moon is slowing down our rotation, and it's not going to budge Jupiter.
How big is Io compared to our moon?
It is, I have a slide of the 7 big moons. Let me pull it up. Be under. Nope, 1 second. Right here it is. Pretty close.
Okay, but Jupiter's just massive compared to the Earth. So.
What's that? I'm sorry?
But Jupiter's much more massive than the Earth, so I see why there's not much of an effect.
Yep.
So do you think there's tides in Europa in the oceans?
That's a good question, and I would imagine, yeah. I've never thought about, when we think about tides, like in oceans, we think about waves, and the waves, being higher or lower, and they may not, they're not going to be able to do that because there's this layer of ice covering the ocean, but probably there's pressure waves going around. I'm sure the ice feels, instead of being lifted up and down like something bobbing the ocean, it's pressing on the ice. More pressure, less pressure, more pressure, less pressure as the waves go around. Yeah, probably.
Well, I'm hoping when we get nuclear fusion, we'll be able to go and see.
Yes.
I feel like that's what's going to take us to the outer solar system.
It's going to be like day and night. It's history, by some measures, history will begin once we achieve efficient commercial fusion. It's a different game. It's a post-scarcity society, essentially.
Yeah, I'm pretty excited.
Yeah.
All right, thank you.
Sure.